I'm Dr. Abby Stevens, the Public Programming Manager at the MSU Museum, and I'm also the Ignite MSU chapter leader. So it has been my pleasure over the last 2 months or so to work with 9 research rock stars who are students here at MSU at various levels, graduate and undergraduate, who are doing research on really, really cool topics. We have people from, I believe, 6 different colleges, and everyone is from a different department. So it's been fascinating to learn all about the work that they are doing here at MSU, and to also help them be able to tell their story to all of you tonight. So I'm going to give a brief overview of what Ignite Talks are, in case someone dragged you here and you're like, that sounds weird. Don't worry, I got you. So for Ignite Talks, they are 5 minutes flat for one big idea. To get those 5 minutes, you have 20 slides that auto-advance every 15 seconds. The auto-advance is, I'm sure the speakers will tell you, the hardest part of all of this. You have to have things well choreographed. Ignite started in San Francisco in 2006, so it has been around for quite a while at this point. Since then, it has been in over 350 cities across 6 continents, and we are the only one currently in Michigan, which is lots of fun. So to get the students who we have for Ignite, we have an open call for students doing research projects in any field here at MSU. Previous public speaking or stage experience is not required. We have a research communication workshop, and we had a dress rehearsal with one of the acting professors, Rob Rosnowski, to help students hone their craft on the stage. We then selected 9 research rock stars and the research communication workshop, and we are looking for more students in the fall. This is our 2nd iteration of Ignite, and we are really excited to do this again in the fall. So please keep an eye out in Museum Communications for the open call for that. So this evening, we are going to start off with 5 talks after I stop talking now. Then we will have a brief intermission where you can use the bathroom, get a drink of water or something, chat with your neighbor, and then we will have 4 talks after the intermission. Interestingly, there is no Q&A involved here. You are welcome to ambush a speaker at the very end of the whole thing, politely, gently, but there's no Q&A following the talks. So it's a very dynamic, fast-paced evening. And with that, I'm going to get queued up for the first speaker. Our first speaker this evening is Alyssa Saunders.
Spoilers.
Here we go.
All right, hi everyone. Like Abby said, I am Alyssa Saunders. I'm a 3rd-year PhD candidate here at MSU in the Integrated Biology Department, and today I'm going to be telling you about the shockingly tailless sperm of African electric fish. But first, let us talk about Abby, save me.
This is part of the fun, everyone. Okay, ready? I'm gonna go to the next one.
Sex. It sounds, it smells, and it's the way by which we and the majority of other animals ensure that our species keeps on keeping on. Sex can look really different for different species, but when you get down to it, you just need 2 things, a sperm and an egg. And when these 2 cells come together, you're going to get a zygote, which eventually will grow into you, or a fish, or an insect, or whatever species that we're dealing with here. The coming together of these 2 cells is known as fertilization. And you likely have some idea about what this looks like in your head, probably something like this. We have a bunch of little sperm all swimming with their tails racing to be the one to fertilize the egg. This kind of cartoon idea of what a sperm looks like is pretty close to what we see in real life. So shown here is a human sperm, and we can see that it has 3 main parts, a head, a midpiece, and then that tail for swimming. But honestly, human sperm is pretty boring, considering that sperm is the most diverse cell type that we know of, demonstrated here by this beautiful collage of sperm from animals across the entire tree of life. exceptions. Oh, they all have heads, midpieces, and tails. I forgot to mention that. Almost all of them, you can see it really well when they're lined up like this, all in the same orientation. But now, as with everything in life, there are exceptions, and this is where tailless sperm comes in. Tailless sperm has evolved just 36 times. 35 of those evolutions have happened in invertebrate lineages, and only once has it evolved in a vertebrate lineage. And that lineage is the Mormyrid electric fish. This is actually a pretty large group of about 230 species found in lakes and rivers across Africa, and they're able to use electricity to communicate with one another and to also navigate through their environments. The sperm of these animals was first imaged in about the early 1970s, and you can see them here. They are these oval-shaped cells with no tail to be seen on them, and this means that they also can't swim or really move on their own at all. So right about now, you're probably thinking something like, if sperm swim to reach the egg in order to fertilize it, then how does Mormyrid sperm even work? It can't swim, it can't move. Well, the answer to this question is, I don't know, but it's part of what I'm trying to find out, starting with getting some updated images with updated imaging technology. Because as you can imagine, microscopes have progressed a lot in the last 50-something years. So in my lab, we've gathered Mormyrid sperm samples, threw it under the scope, and here's what they look like. As we expected, they're these little oval-shaped cells, and our images here just doubly confirm, yep, there's definitely no tail on these things. Now, there's actually a pretty big piece of this puzzle that we haven't chatted about here yet today, and in fact, no one has really studied before at all, and that's what these tailless sperm are actually fertilizing, Mormyrid eggs. So we've also collected some eggs in my lab and imaged them, and here you can see the surface of an egg, and pointed out is the hole where sperm is able to enter, and notably, there's a little bit of a difference in texture around that hole versus the rest of the egg. So then, if you were to go ahead and zoom in to an area near that sperm entry point, what you're going to see are a bunch of even smaller holes, just used for things to move in and out of the egg, but also all these little tufts of hair scattered across the surface. Then, if you were to go ahead and zoom in to a point that's further away from that sperm entry point, you can again see a couple of those holes used to move things, but now you can also see longer versions of those little hairs. So the question is, what are these things doing? Well, if we compare to other fishes, some of them have long egg hairs used to attach to surfaces. Mormyrid hairs are probably too short to do this, but some fish have these kind of features like spirals that guide sperm to the entry point, so maybe they do that. So why do you care? Well, on the practical side, issues with sperm tails are a common cause of infertility, so by studying tailless sperm, we may be able to find mechanisms that lead to sperm tail loss, and that could be something to look for in humans as well. But on the more fun side, biology is weird, and I think that there's inherent value in studying our biodiverse planet and understanding the beings that we share it with, like little fish that make electricity and sperm without tails. Thanks.